let's move even further. So yesterday we studied when reactions get off equilibrium and the freeze-out occurs. And we've seen the simple criteria that we always used, meaning reaction rate, the comparison that goes between the reaction rate and the expansion rate of the expansion of the universe. And we further developed this idea by getting a full equation that describes the entire behavior of the reaction. That also goes with the speed, how it proceeds, and so on. Of course, it's not like a sharp transition between the equality or inequality between those two terms. And that equation was the Boltzmann equation. So you see it's like a continuity equation, which terms on the left-hand side, if placed equal to 0, will give you number particle conservation, right? This was an n dot equal to 0, would be particle conservation. The number density of particles for a given volume is not changing. For every co-moving volume is not changing. Then we introduced a source term that had creation, the number of particles of one type and of the other type. And then we had the destruction of the particles with another factor, beta, and the other particles that are on the other side of the equation. That's what we have seen. Then we elaborated more this concept, but that's the key idea, right? So we have the time evolution of the number density of a co-moving volume equal to 0, the number of particles is conserved. So this is a continuity equation expressing number density conservation, no destruction or creation. We introduced a source term with creation and destruction. And then we have seen how we linked these two parameters through the equilibrium. So the two are linked. Right? That's why in the end we got those ratio between the particles at equilibrium and in non-equilibrium. Then we encountered the first application of this equation, of the Boltzmann equation, and we studied the freeze-out of dark matter. Right? And therefore the creation of relics. Particles first follows the evolution of the universe. It expands. We are going through a sequence of different equilibriums, states. That's why the number of particles is changing. Okay, so that's something that asked me somebody yesterday. Let me stress this a little bit more. So the thing is that we have the universe is in an expansion phase. Okay, and if the reaction rate is larger than the expansion rate, then we have an equilibrium for our particles. That's clear. Okay. The thing is that this guy has a function of time. Therefore, you should consider the number of particles at equilibrium at a certain time. Okay? If we freeze the universe, then those numbers are fixed. Creation and destruction are in equilibrium. If we change the temperature, we are in a different equilibrium state. Okay? And therefore, the number in equilibrium of this particle is going to be different than in the previous equilibrium state. And of course, we have a smooth transition, right? The universe has always the time to re-equilibrate itself when this condition is met, okay? But the number in equilibrium is changing as a function of time. Then another concept another question that I got was the fact that at a certain point we have the number density in equilibrium with respect to the number density, and this one was dropping. So we had like a number density of species x, and then that's for the other standard model particle. So this is like this. So that's in equilibrium. That's not in equilibrium. At a certain point, I did that. And then you ask, but why? Here we are studying the breaking off of the equilibrium. Why this one is still in equilibrium? Because that's not the only reaction that took place. We not only had the reaction of our dark matter particle, whatever it is, self-annihilation, equilibrium or not, and then we have standard particles on the other side. Remember that these guys are interacting with other particles. Let's say that L is equal to the electron, for example. What is this guy reacting with? With the neutrinos, with positrons, with protons. and so on and so forth, with photons, if this is a charged particle, right? And the equilibrium is with these guys, okay? So this one is going to be in equilibrium. That's why I dropped. So it goes off equilibrium with this reaction, with dark matter, but this one, we are assuming to be still in equilibrium because there are all of those other reactions. Okay? Just to clarify something that we've seen yesterday. Then there was one of you, and I don't remember whom, told me that there was a mistake, but actually it was correct. I didn't give myself the time to verify that what I wrote was correct. But what was concerning the number density of particles and the comoving number density of particles. So number density of particles is the number of particles over a volume, which is the number density of e to the power of 3 times the comoving volume. And therefore, e to the power of 3 for the physical number density of particles is the number of particles over the comoving volume that we define as the comoving number density. Okay, so of course it's E is on top of it because we have this reverse relationship. Okay, just that, just how the volume scales with respect to the scale factor. All right, and the power of 3, of course, because it's a three-dimensional volume, right? All right. Then, having all these ideas, we also studied the freeze out of, the break off from equilibrium of the neutrinos and the electrons. So we have the formation of the cosmic neutrino background. And then we studied the reheating phase that is due to the annihilation of electrons and positrons that follows that follows the freeze out of neutrinos for the creation of the cosmic microwave background, or the cosmic neutrino background. Okay? Now we continue and we study a little bit better or in more depth the reactions in equilibrium. And actually, reactions that among the products have photons. Okay, that is going to be extremely important for the Big Bang nucleosynthesis and for the recombination and the formation of the cosmic microwave background. So it is a reaction with photons, and the equation that is going to rule the number of species in equilibrium is given by the Saha equation. Okay. So, all right. So, let's give a look at which phase of the universe we are. So here we already passed these highly energetic phases with these annihilations, the neutrinos, and so on and so forth. The universe proceeds as a function of time. The temperature goes down, goes down, goes down, lower and lower energies. Okay? At a certain point, we are going to have protons, neutrons, electrons, positrons, those that are left, are going to be non-relativistic. And the relationship to understand if a species is relativistic or non-relativistic, it depends on the mass of the particle, where E can be any of those. That's the energy of the particle, and we always make the comparison with respect to the thermal energy, and is non-relativistic whenever we have this relationship holding, right? So the mass of the particles is fixed, the temperature goes down, at a certain point this one is going to be larger, so the rest energy is going to be larger than the thermal energy that is related to the kinetic term of the particles, and they're becoming non-relativistic. So that's what the limit we are going to consider. Okay? Right. Then what we are going to learn is that for this equation is extremely important the ratio between the number of baryons and the number of photons. Okay? It's going to be key for this equation. And for that, we need to study, basically, the relationship between the baryons and the photons. Because we have the photons. The photons are among the equations that we are going to consider in the following. So let's study, first of all, the baryons to photons ratio. No. Okay, so that's the number of baryons divided the number of photons. So how we do it? Well, it's easy. We know what are those distributions as a function of temperature. We just plug them in. We can plug them in, plus we have observations, because we have constraints. From observations. So we have, for the baryons, we have estimates, for example, from the large-scale structures that we are going to meet and learn, from the cosmic microwave background, and from the galaxy clusters, from clusterings of galaxies, and so on and so forth. We can, for simplicity, assume that baryons have all the mass of the proton. Here we have our number density that we can measure, omega b, divided MP that we are leaving, and just for the definition of the energy density, I have to multiply for the critical density. This one, by the definition of omega b, is rho b. And that's roughly rho b over the mass of the proton. And then we have the definition of the critical density, 8 pi g. And once we plug in the numbers, because this is a measured quantity, this is a measured quantity, so we evaluate it at time 0, or at the time that we want, we have 10 to the minus 5 omega m h to the power of 2 centimeter to the power of minus 3, where omega b, from our measurements, is roughly 4% of the entire energy budget of the universe. So that's our measure that we plug into here. So we have this number. Then we go for the photons. That's easy. We have our relativistic species. We computed it nowadays, as we did for the other one. So let me plug the 0 here. So we have g, then psi 3, or pi to the power of 2, kt over h bar c to the power of 3. That's we studied when we did the quantum gases, right? And of course, that's at time 0, therefore we need to plug in the temperature of the photons nowadays. Where we get that number? From the cosmic microwave background that we are going to learn. For the moment, just know that this is a measurement that we can do, and the T0 is the temperature of the cosmic microwave background, so these millimetric photons that we are measuring, and that's what we get, 2.752, etc., 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 Kelvin. And also this one is measured. And what we do, we just plug these two numbers together. We plug these two numbers together, and what we obtain is that nu is equal to 2.7 10 to the minus 8 h to the power of 2. And is a constant. Okay, for baryon conservations and for the fact that these are the number of photons that are relics. Remember, these are relic density of photons, and their number is conserved. They're not anymore interacting with anything else. They're just living their life without any trouble anymore, right? So that's the number that we get. 10 to the minus 8, that's small. And since this is the ratio between baryons and the photons, this means, if this number is very small, that the number of photons is much larger with respect to the number of baryons. That's why the baryons represent the temperature of the universe, if you wish, okay? They are the reservoir of the temperature for the interactions that we had. And in fact, the temperature of the photons were the one leading all the equations that we used so far, all right? So that's the number. And this is, keep in mind this number, okay? It's coming back when we're going to do the Saha equation. All right. Now, which kind of interactions are we interested in? As I said, A is getting larger and larger. The universe is expanding. The temperature is growing, is going down. Therefore, the energy, yeah?
What is the small h squared?
See, yeah, this comes from the very first lectures that we did, right? So we have the Hubble factor, or the expansion of, for example, we have h naught, right, that goes into the Friedmann equations as a proportionality constant, telling us how fast the universe is expanding nowadays. And this can be parameterized as h times 100. Okay, that's it. So this is just you know, for convenience, this is used. And that's used, this was introduced especially for the reason that this number was very, very unclear. So now it's, I mean, we are at the percent level of accuracy, so we kind of know the number, but till the, I don't know, let's say 2000s and so on, it was a very, very uncertain number. And therefore, it was always used, all the quantities as something h, the mass h. That's because it's easier to incorporate this ignorance in this number. And you make your measurement, you want to know what is nu according to your measurement, and you plug your own h there, okay? Just for convenience.
I was just wondering, because now eta has a unit, right?
H is a dimensional. So the units are in h naught, are in the rest, okay? So here you have all the other units. This is just an adimensional quantity. Yep.
The equation for n gamma 0, what is the
Wait. Where?
for n gamma 0 in the
Here?
yeah,
That's the number of photons.
and on the right side is L.
G, yeah, the L, this is a fixed number. This is a special function that is evaluated at 3. So this is just a number. Now, if you ask me what is the number, I don't know, okay? But it's just a number.
So it's not a rounding.
No, that comes out from an integral. It's a special function. You find it in the derivations that we did at the beginning for the quantum gases. All right, so that's what's happening. The energies are going down. The energy of the photons, therefore, are getting lower and lower. And this means that photodissociations of particles and compound particles is getting less and less efficient, up to the point where photodissociation can basically drop. Okay? And we have the formation, for example, of heavier elements. So we are going to have the Big Bang nucleosynthesis, where we are going to have reactions like proton plus neutrons, and we are going to have the formation of deuteron plus the emission of a photon. Okay? And deuteron is just H2. So it's a particle composed by a proton and a neutron. That's an isotope of hydrogen. That's what deuteron is. Then we are going to have also the formation of tritium, which is another isotope of hydrogen, which contains 2 neutrons instead of N or 0 for hydrogen. And then we are going to have the formation as well of beryllium, lithium, helium-3, and helium-4, which is going to be the final product through a chain of reactions that we are going to study. The key point for the BBN is that we start with this reaction, which is the one that allows that allows the other reactions to take place. Without the deuteron, Big Bang nucleosynthesis wouldn't work, and we wouldn't have the formation of helium-4. Okay? All right. Then the other reaction that is going to be relevant for this discussion is recombination. Recombination, where the reaction is going to be between protons and electrons. The temperature goes down. You see, when we had this sort of, say that we form deuteron, which is this compound particle. When the energy was extremely high, a photon kicks in and gets photodissociated. All right? Temperatures are low. Now this guy can glue together and remains as a bound state without being photodissociated anymore. Right? This is true and simpler to understand for a photon because we are used to ionization of atoms. In this case, is the inverse process. It's not ionization, but it's going to be a release of a photon. Right? So in this direction would be an ionization process. Hydrogen, neutral hydrogen, is get kicked by a photon. You get the electron kicked out from your atom. The process is going to be in equilibrium. At a certain point, the equilibrium is changing, and then will also be break off. Okay? We are going to study, in this case, these two reactions in equilibrium. In equilibrium, which, as I stressed earlier, it doesn't mean that the number of H is constant. That's because there is a temperature evolution. All right? Same goes for, so that's for, let's put it here. So this doesn't mean that, for example, the deuterium is not going to be constant because it changes as a function of time. So we have different equilibrium states. The same goes for the hydrogen, for the formation of neutral elements. Okay? The name is a little bit misleading because it's called recombination. But actually, they have never been combined before. Okay? Don't ask me where this name comes from, but it is the first time that protons and electrons combines in a bound state, meaning an atom. Okay? In any case, it's called recombination. So you see, these are two reactions that involve a photon among the products. Okay? And those sort of reactions in equilibrium are described by the Saha equation. All right, so let's derive the Saha equation. Saha equation. All right, so the reactions that we are going to consider, as I said, are of that type. And for full generality, I'm going to call the particles, not electron, positron, and whatever, but E, J, and the reaction is going to have an interplay with the particles K and a photon. That's the only one they specify. The other ones are some reaction that take place to this game. The other one is a photon, always a photon. Okay? That's the point. All right, so E, for what concerns us, are going to be the electrons, are going to be the neutrons, are going to be the protons. Okay, and the helium. All right. Then we have equilibrium. And what we did study about the chemical potential in equilibrium. So we have an equation that relates the chemical, the sum of all chemical potentials, and the total sum has to be 0 in equilibrium. We have seen that when we studied the ground canonical ensemble. So we are going to have the chemical potential for the particle E plus the canonical potential for the particle J, it has to be equal to the canonical, sorry, to the chemical potential of the particle called K and the chemical potential of the photons, which, again, we have already learned that is equal to 0 in equilibrium. We can create an arbitrary number of photons, okay? The number of photons is not constrained. Then, what I said is that in the regime of temperatures that we are considering, we are in a non-relativistic regime. Therefore, except for the photons, of course, all the rest can be treated with a non-relativistic approximation. This means that we can use the Maxwell and Boltzmann distribution for the number density of particles. Max and Boltz distribution that I write here. So for the species E, that's valid in equilibrium. That equation is valid in equilibrium. That's for an equilibrium. It's anyway equal to GE. So these are the internal degrees of freedom minus E KT over 2 pi h bar to the power of 2 to the 3 and then we have the exponential, which involves the chemical potential minus the energy, the rest energy of the particles, divided the thermal energy, KT. That's the Maxwell-Boltzmann distribution. Now, for convenience, let me call all of this thing here lambda to the power of 3 half. This is just to ease the computations later. Okay, but it's not a constant, there is a temperature here, okay? All right. And it depends also on the particle. So let's call it lambda E, because there is the mass of the particle. All right. So now let's keep the temperature out. Sorry. Let's do like this. So all of the things that are not related to the... let's write it. It's easier. Lambda to the 3 half. Is going to be KT over 2 pi h bar to the power of 2. Okay? Definition. So just to simplify the life with KT to pi h bar to the power of 2. Okay, what are we considering now? Reactions, right? And for the reactions, we are looking for the ratios between the number density of the various species that are involved in our reactions. So we can define this big X that is a function of temperature. So just to stress the fact that as T is changing, the ratios that we're going to get are going to change. And this is the number of particles E times number of particles J and number of particles K. That's in equilibrium, equilibrium, equilibrium. So we define this number. And then you can ask me, where are the photons? They are part of the reaction. Yeah, but now what I care about is about how we go from this particle to the creation of this guy here. Then a photon is emitting, no problem. And you say, but you're ignoring it. No, because remember that the temperature of the universe is ruled by the photons. This comes from the fact that we have 10 to the 8 photons for one baryon. Okay, they're ruling thermically. Therefore, in this equation, if I write it like this, the photons are there. Where are they? Here. And here. That's T of the photons. Photons and photons. So the important rule of the photons is in the temperature, in setting the temperature. All right. So now what we do, we have this equation that we want to evaluate, and we plug in the numbers that are coming from the Boltzmann equation. We just plug it here for all the species. That's it. Okay? Let me, yeah, it should fit here. So let's do it. So we have GE Gj over Gk. So you see, I'm respecting this order, proportionality with respect to the G. Then we have lambda to the power of 2, lambda to the power of 2 divided lambda. Here we have a lambda contribution, here one lambda contribution, and we have this simplification. Then we have the ratios between the masses. So we have mass of the particle E, mass of the particle J, divided the mass of the particle K to the power of 3/2. And then there is the exponential. Yeah? No. Lambda is not there. Okay. Then we have our exponential, where we have, so it's going to have the product of exponential, is an exponential of the sums. Remember, just a property of the exponential. So we have the mu E plus mu J minus mu K. There is the minus because it goes at the denominator. It is exponential for the K particle. And then we have the minus me c squared minus mj c to the power of 2 plus mk c squared, all divided by kt. And what we have from equilibrium, that this guy is equal to 0. So this one disappears, no surprise, right? We are in equilibrium, the total mu is equal to 0, right? In fact, mu do not appear in the Boltzmann distributions. Here I just included to show you and stress the fact that this is going to happen even if you have a different kind of chemical potentials playing in your fluid. All right. And basically, that's it. This is what you are left with. Plus, we can make a consideration on this guy. You see, we have the difference between the rest energy of the particles on this side of the equation and minus the particles, the rest energy of the particle that is considering this ratio on the other side of the equation. That's the energy difference that you need to create the photoionization. So that's, or better to say, that's the binding energy that is keeping those two particles together. If you exceed that amount, you get your photo, or you're getting to have an unbind structure. So E is M1, Me plus Mj minus Mk c to the power of 2. That's your binding energy. All right. Then what we do is to, because in the end we want to see what is the dissociation rate in the case of BBN, or the photoionization rate in the case of reionization. It's the same, two different names, but it's the same thing, just terminology. And to compute the ionization rate or the dissociation rate, it's usually everything expressed in terms of ratios, right? It's a Therefore, we define NE over NB. So we are counting how many of the species E are going to change with respect to the total number of baryons and B. Having that, so that's the dissociation fraction. So you understand if this number is a constant, then is 1, sorry, then it means that everything is like a baryon, using this bound state. Otherwise, not. Okay? So anyway, anyway is renormalized with respect to NB. That's convenient for the photodissociation. All right. Then what we can do is to relate the number of baryons to the number of photons through our nu that we evaluated earlier. Where is it? There. So that's just the ratio. Therefore, that's nu times the number of photons. We know what is the distribution of the number of our photons. Therefore, we're going to have nu. We just plug it in. 2 internal degrees of freedom. 3. And then pi power of 2 kt over h bar c to the 3. And that's, and I did that to plug in this number. So you see, everything now contains the photons here. Here we have the number density of photons. It enters here. Okay, so not only through the temperature, but now I'm also considering the number of photons through the factor nu. So what we do, we just continue with this equation. So Ne Nj over Nk, and then we used this definition. So we have Ne equal to Xe times Nb. So we have Nb to the power of 2, Xe, X2. The power of 2 because we have this product. And then we have Nb x for the particle k. This 2 goes away with this one. And of course, is the very same expression, where now we have our Nb that popped up. Then we have kt over 2 pi h bar to the power of 2, 3/2, the ratios between the masses, and then there is the exponential, minus kt. Plugging in our Nb here, what we get is, well, I stop here. Let's stay generic like that. Oh, yeah, let's plug it in. Let's be pedantic. Ge, Gj, nu, Gk, and then we have pi to the power of 2, 2, 3, Me c to the power of 2, that's the energy, kt to the power of nothing, e to the minus e over kt. That's important, okay? This one is very important in defining when the reactions are going to be of equilibrium, okay? Why is that? It's like that because that's something that I told you already n times. We have our reaction rate, that's the temperature, that's the rate of the reactions, and that's the Hubble rate. Fantastic. Now look at this number. You see we have a proportionality for this term, so here we would have the reactions rates. If that number is pumped by the fact that we have a very large number of photons, so nu is, remember, is baryon over photons, 10 to the minus 8. It means that this equation is multiplied with this nu, which is a 10 to the, 1 over nu is 10 to the 8. This guy goes up. Okay? So if I change the nu is small, it goes up, nu is large, it goes down. All right? And what you see is that the reaction is delayed. So you go off equilibrium, the reaction stops. Afterward, as the smaller the nu is, the more delayed the end of the reaction is. That's called a delayed reaction. And that's due to this guy. Okay? You change this number, this gamma goes up or down. In our case, we have gamma very large, therefore is very much pumped up. We have a pimped reaction rate. All right. And here we are. So that's the basics that we need to compute the reactions in the BBN, in the Big Bang nucleosynthesis, and for the recombination. So a little recap, then I will clean the board, and we will go through the two processes that I just mentioned. So that's the reactions that we are going to consider, something that goes with photons, okay? Dealing with photons that are the ruling species of the universe is extremely convenient to link all our quantities to the photons as much as possible. One is the temperature. They are ruling the temperature of the universe. The other one is their number, which is crazy large with respect to the number of baryons. Therefore, whenever we have the number of baryons and the number of photons, they're both conserved because they are relics, okay, at this stage, we are going to have, we can define this nu parameter. By observations, through observations, we know that, the number is extremely in favor of the number of photons. Then, these are the two reactions that we are going to consider. Big Bang nucleosynthesis, the first one is quite in equilibrium, so proton plus neutron. The temperature is low enough to allow the binding of these two particles into an atom of deuterium, which is an isotope of hydrogen. Then there are other reactions that I'm going to describe later on, which are not quite in equilibrium, okay? But this one is the key one that is ruling, tuning everything. Then we have the recombination, in which, again, we are in a much later stage in the evolution of our universe, where the temperatures are much lower, and now are the electrons that are going to bind with the protons, forming neutral hydrogen. Neutral hydrogen and emission of a photon. Okay? At that point, the number of free electrons in the universe is going to be basically 0. It's not 0, of course, but it's going to decrease by a substantial amount. And this has consequences on the life of photons as well. But that's for a later stage. To describe that sort of equations that are in general written in this way, we use the Saha equation. Saha equation that describes these reactions in equilibrium, where the total chemical potential is 0, where the chemical potential of the photons is also 0, and we consider non-relativistic species and approximations for the distribution of the number of particles, the number density of particles, because the temperatures are low enough, so the thermal energy is lower with respect to the rest energy of the particles that we are considering, including photons, including electrons. All right? So Maxwell and Boltzmann distribution. What we're going to look at is this quantity, which combines the ratios between the number of the species E and J over the number of the product particle K. The photons are not disappear by this expression because they are hidden into the temperature, which is ruling the entire universe. So they are setting the temperature of the universe. Then, what we did, furthermore, was to link the number of baryons to the number, we computed an equation that concerns ratios with respect to the, this is a mistake, because what I did was to get this guy and bring it on the other side. Okay, so this is gone. So up to here, there was the NB, and then I brought the NB on the other side. Okay, sorry, let's correct it now. All right, By doing that, we have this parameter, which is the constant that we constrain observationally, and tell us that the crazy large number of photons are going to delay the end of this equilibrium. The reaction is going to take longer than what should be just by looking at the ratio of the binding energy and the thermal energy. Okay? Without this term, this one would be kind of the ruling one, if you wish, and the binding energy is equivalent, and you basically have, whenever the temperature is closer to the binding energy, then you have your reaction, right? This is boosted, and the reaction can take longer. Why? Because the energy of the photons has a distribution. It's not a delta, right? It's not that the universe has a certain temperature and that's it. All photons has this energy. No, they have a Planck spectrum. They have a Planck spectrum, so if we go for the frequencies, that's our spectrum. Let's call it P. And it's something like that, the Planck distribution, right? If the temperature is going down, the peak is moving in this direction. So as the temperature decreases, the Planck spectrum does something like that, okay? It moves like that. So the temperature here is larger than the temperature here. T2 smaller than T1. But there is this tail. So if you see that there is always a tail. If you have a very large number, the spectrum is very large and is in this tiny tail. Yes, is a tail with respect to the overall distribution. But since their number is so large, it's still relevant. Okay? Say that I have a ratio that with respect to the rest of the population, which is 1/1000. But if I have multiplied this 1/1000 times 10 to the 8, still the number is large. And therefore, we still have a population of high energetic photons that can photodissociate the two particles that are trying to bind together. Okay? Key concept, temperature goes down, the energy of the photons is going down, dissociation is decreasing, but since there are so many that they are still populating the tail of the Planck spectrum of the distribution of the energy of the photons are still relevant to photodissociate this guy, therefore to make the reaction go in that direction. All right? Good. That's it. So let's stop here. We can resume at 15. And we are going to look at the